All right, so today we're going to talk about section 3.7. This is on rational functions. I may try to break this up into multiple videos. We'll see as we go along here. So the idea here is that in the previous sections, we've built polynomials based on the positive whole number power functions. In this section, we're going to explore functions that are based on power functions with negative integer powers. These are called rational functions. And also, we're going to just explore things that have that are the ratio of two polynomials. And those are what we will call rational functions. Let's look at a particular example of where a rational function might arise. Before we get into a definition of it, let's talk about what these things really are here. So, you plan to drive 100 miles. Write a formula for the time that the trip will take as a function of the speed that you drive. So, of course, if I multiply speed times time, I should get the distance I travel, right? So let me change that. Let's let t stand for time. And let's have v be our velocity or our speed. And I guess we can have d for distance. Or maybe, let's see. Yeah, that's totally fine. Actually, we don't even need to define a variable there. Well, with this information, I know the distance that I travel is equal to the speed at which I travel times the time at which I'm traveling at that speed, right? If I'm traveling at 60 miles per hour for 2 hours, then I went 120 miles. So I know that the distance that I plan to drive is 100. So this is equal to v times t. I want to find a formula for the time that the trip will take as a function of the speed. In order to do this, I just isolate the t. I divide both sides by v, and I get that t is equal to 100 over v, or we could write that as 100 times v to the negative 1 power. So this relationship can be written using this negative exponent or by writing this as a fraction. This particular example is an example of an inverse proportional relationship. Let me make this larger. This is where one quantity is a constant divided by another quantity. For example, exactly what I have here, or maybe something like y equals 5 over x. This would also be an inverse proportional relationship. Several natural phenomena, such as gravity, gravitational force, and the volume of sound, behave in a manner that is... Let me get the box here. Inversely proportional to the square of another quantity. So this is something like if for example, the volume V of a sound heard at distance d from the source of the sound would be related by the expression V equals K divided by D squared, where K is a constant. K is some constant value. These functions are transformations of the reciprocal squared function, f of x equals 1 over x squared. Inversely proportional relationships are just transformations of the reciprocal function, which is f of x equals 1 over x. So we can look at the graphs of these things, and we can determine a few kind of basic properties of how these things behave. So on the left-hand side here, I have graphed f of x equals 1 over x. And on the right-hand side, I have graphed f of x equals 1 over x squared. Let's look at this left-hand one. Let's look at this 1 over x squared. And let's talk about the short-run behavior of it. Or, sorry, I misspoke, I believe. I meant 1 over x, not 1 over x squared. This left-hand one is the graph of 1 over x, right? So, actually, I guess before we jump into the short-run behavior, just notice that in both of these graphs, as the graph gets closer to 0, I have these two branches of this graph that they're not actually ever attaining an x value of 0, right? It looks like both of these functions are actually undefined at 0, which makes sense because if I plug 0 into either of these functions, then I'm dividing by 0. I can't divide by 0, so both of these functions should be undefined at 0. So if we look at the short-run behavior of f of x equals 1 over x, we might notice that as my input values approach 0 from the left-hand side here, so as I come in from the left-hand side of this function, notice that as I get closer to 0, my y values are going downwards. So notationally, the way I represent this is as x approaches 0 from the left, I use this superscript minus sign to denote approaching 0 from the left side of the graph. F of x is going downwards. It's going down towards negative infinity. Similarly, as x approaches 0 from the right, as I come in from the right-hand side of the graph, and my x values get closer to 0, this graph is going upwards. So I denote this as x approaches 0 from the right, the superscript plus sign represents from the right-hand side of the graph. F of x approaches positive infinity as the graph is going upwards. This behavior creates what we call a vertical asymptote. At x equals 0. I'm going to underline vertical asymptote. We're going to get a formal definition of a vertical asymptote in a second, or in a few minutes, but an asymptote is a line that the graph approaches but doesn't touch or cross. So we see that this graph is getting very close to the line x equals 0, the vertical line x equals 0, but it's never going to cross that line. Now let's look at the long run behavior of this same function. So as I go farther and farther to the left of this graph, notice that these y values are getting really close to 0 over time. Really close, right? They're kind of leveling out to 0. So in other words, as x approaches negative infinity, f of x approaches 0. Similarly, as I go farther and farther to the right of this graph, what's happening here? Well, as I go farther and farther to the right, it looks like these y values are also getting closer and closer to 0. So I denote this as x approaches positive infinity, f of x approaches 0. So this behavior, notice how my long run behavior is really the same on both sides, right? This graph is leveling out to the same y value as I go out towards positive and towards negative infinity. This behavior creates a horizontal asymptote. Well, they're getting closer and closer to this y value of 0, so this is at y equals 0. So in other words, this graph is getting closer and closer to this horizontal line of y equals 0 as my input becomes very large in the negative and in the positive direction. Oh, I actually discussed both of those already. I don't need those extra pages. And here we have these definitions of vertical and horizontal asymptote. A vertical asymptote of a graph is a vertical line. Remember, vertical is up and down, right? Where the graph tends towards positive or negative infinity as the inputs approach A. So once again, the vertical asymptote of a graph is a vertical line x equals A, where the graph tends towards positive or negative infinity as the inputs approach A. Notationally, we can say, as x approaches A, f of x approaches positive or negative infinity. It depends on the graph and how that graph is behaving at that asymptote, right? A horizontal asymptote of a graph is a horizontal line y equals b, where the graph approaches the line as the inputs get large. So as x approaches positive or negative infinity, f of x approaches b. And this should be the same for as x approaches negative infinity and as x approaches positive infinity. If I have a horizontal asymptote, I should be approaching the same y value for both of those. Let's move on here. Let's look at this definition of a rational function. A rational function is just a function that can be written as the ratio of two polynomials. Then this is like a very formal like math definition. This is just one polynomial divided by another polynomial. A rational function is the ratio of two polynomials. That's it. This looks scarier than it actually is. So let's go ahead and look at an example here. A large mixing tank currently contains 100 gallons of water, into which 5 pounds of sugar have been mixed. A tap will open, pouring 10 gallons per minute of water into the tank at the same time that sugar is poured into the tank at a rate of 1 pound per minute. Find the concentration in pounds per gallon of sugar in the tank after T minutes. All right, so here we have some important information. Let's make an equation for the water, and let's make an equation for the amount of sugar in this tank. So a large mixing tank currently contains 100 gallons of water. So it's starting with 100 gallons of water, into which 5 pounds of sugar have been mixed. So we're starting with 5 pounds of sugar. These are our initial values for these two equations that we're going to set up. A tap will open, pouring 10 gallons per minute of water into the tank. So what this is telling me is that 10 gallons of water are poured into the tank every minute. So I'm going to write plus 10 times T, where T represents time in minutes. At the same time that sugar is poured into the tank at a rate of 1 pound per minute. So this is plus 1T for this sugar equation here. And really, I could write this as just plus T if I wanted, right? If I'm multiplying something by 1, I don't have to write the 1. So the concentration in pounds of sugar per gallon of water is going to be, we can call this, let's call this C of T for concentration. This is going to be the sugar equation divided by the water equation. And this is just 5 plus T divided by 100 plus 10T. And this is an example of a rational function. Let's look at finding asymptotes and intercepts of rational functions. So if I want to find vertical asymptotes, actually perhaps at this point I'll start a new video to make this a little bit shorter. Okay.